and mechanics. And it all comes down to good old Newton and his laws of motion. Of course, he wrote them down in Latin. So there's the first law, corpus omni perseverare. Yeah. For those of you who don't understand Latin, there we go. Everybody continues in its state of rest or of uniform motion in a right line unless it's compelled to change that state by forces impressed upon it. So basically what it's saying is, if you're standing still, you will remain standing still unless someone pushes you. That's essentially what it's saying. And it's saying, if you're moving, you will continue moving unless someone stops you. That's probably the easiest way to explain the first law of motion. The second one is probably the most famous of them all, and I'm sure you recognise it. The motus proportionality, however you say proportion. Yeah, I won't even try and say it. But that is, of course, this one. The change of motion is proportional to the motive force impressed, and it is made in the direction of the right line in which that force is impressed. And I'm sure you're quite impressed now too. So what are they saying? Motive force is proportional to the change in motion. That means force is proportional to acceleration. Change in motion, change in velocity is, of course, acceleration. So it must equal some constant times acceleration. And aren't we lucky that that constant turns out to be mass? So force equals mass times acceleration. And then the third one, probably one of the most misquoted of the laws, the actione contrarium. To every action there is always opposed an equal reaction, or the mutual action of two bodies upon each other are always equal and directed in contrary parts. It's often quoted as, to every action there's a, how do they say it? To every action there's a reaction or something like that. Equal and opposite reaction. That's how it gets summarised, but that's actually what it's saying. Vectors and forces. So why do we spend so much time looking at vectors? Probably because of this. Because forces are indeed vectors. Okay? They have a magnitude, they have a direction. Okay? Any force that is not vertical or horizontal, to make the problem easier, we resolve it into vertical and horizontal components. And then we're just dealing with straight line motion, and straight line motion is very easy to handle. The original force will be the hypotenuse of the right angle triangle made by the components. So resultant vectors. Remember, a resultant vector is simply the sum of all the component vectors that act at a point. So if I've got a point like this, and it's got two forces happening at different angles, one of 3 newtons, the other of 5 newtons. By the way, newtons is spelt with a little n, not with a capital N. The unit is capital N, but the actual unit itself is spelt with a little n, even though it's named after a person, and of course his surname is capital N, but anyway, just a little bit of English there. So here we have it. So in other words, I can look at the resultant force and get it this way. Well, I've gone off at 60 degrees, 3 newtons, and then I'll add that vector of 5 newtons to it. Where I ended up, there's my resultant force. I could then go, well, hang on, if that's what it is, I can work out that that angle is 135 degrees. And that angle there, that'd be nice to know what that is. But that one will be 60 minus theta, I know that. I can use my sine rule to work out my angle. It's about 28 degrees is theta. So in other words, the direction of my vector turns out to be 32.59 degrees. What's the magnitude? Well, I can use the cosine rule to find the magnitude. And eventually, once I plug it all in, I get 7.43. That's doing it without resolving it into horizontal and vertical. Let's do it the sensible way. Good old Bob has a horizontal component and a vertical component on the 3 newtons force. It also has components on the 5 newton force. If I was to put it all together, but just look at the vertical, then we have a vertical one of 3 sine 60 and also 5 sine 15. Horizontally, I've got 3 cos 60 and 5 cos 15. If I was to pull it all together, there it is in its two components. I've got the I direction and I've got the J direction. I can find the magnitude of my vector now. That's a lot quicker than using the cosine rule and having to find the angles and all that sort of thing. And the actual angle, I can use basic trig, tan theta, 32 on 59. Okay. So resolving into components will save us a lot of time when we're talking about multiple forces. So what are types of forces? We're going to look at all sorts of different types of forces. We have resistive forces. Okay? Whenever a body moves in some medium, and basically we're always moving in some medium, other than I guess a vacuum, so air, water, etc., it's going to be subjected to a resistive force, and resistive forces are always opposed to the direction. That's Newton's third law. Resistance is always proportional to the power of the velocity. It's usually v or v squared. Okay? But it'll always work. So in other words, the faster you go, the greater the resistance. Imagine, I guess swimming is probably the easiest one to imagine it in when you're in the pool. Faster you go, the water provides more resistance as you swim. So it's generally going to be kV or kV squared, one of those two. Okay. We have gravitational forces, also called weight. So the force of attraction from the Earth, or any object for that matter, but from our Earth we call it the force of gravity, and it's the weight of the object. There is a big difference between weight and mass, of course. Force of gravity then is just mg, mass times acceleration. Forces appear in pairs. Back to Newton's third law again. If an object A exerts a force on object B, then object B will exert a force on object A in the same magnitude, but in opposite direction. Again, Newton's third law. That brings us to these things called contact forces. So whenever an object is in contact with a surface, then there will be a force at right angles, remember I said in the right direction, at right angles to the surface it is in contact with. So that's the normal contact force, or simply the normal force. Frictional forces. So when you're sliding over a surface, the frictional force will have some limiting value. So that's the size that the force can't exceed. It acts in a direction opposite to the motions. Friction acts in opposite direction to motion. So the limiting friction will be some constant times that normal force. So mu, I've just called the coefficient of the friction, whatever the multiple happens to be. Tension, that's when we talk about string. Well, we call it string, but it could be a chain, or it could be anything that's joining an object. But it will exert a force in equal magnitude, because they're in contact with each other, of the objects attached to it. Force along the line of the string and directed inwards, in other words, away from the object. Away from the object. That's what we call tension. In most problems, it's usually better to treat the direction you're travelling as positive. So you need to get it out of your heads that going right is positive, going left is negative, or going up is positive, going down is negative. It's just whatever direction I'm travelling in, that's what I'll make the positive direction. Just makes life easier. Then resistance will always therefore be in the negative direction. Always, 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 can I stress that enough? Always draw yourself a force diagram so you can see what is happening. Let's have a look at this. We have a heavy box, mass 32 kilos, has a handle on one side. Two people are going to try and move it across the floor. One is going to pull it horizontally on the handle, and they'll be able to apply a force of 20 newtons. The other person is going to push it from behind with a force of 25 newtons, but unfortunately the box does not move. Draw a diagram of all the forces acting on the box. So there's Bob, good old Bob. All the forces. Okay, well, someone's pulling it with a force of 20 newtons. Another person's pushing it with a force of 25 newtons, but they're both going in the same direction. But it's not moving. What's stopping it? It must be the frictional force. That's the resistive force in the opposite direction. So call it the resistive force, call it friction, call it whatever you like. But it's just a force going in the opposite direction. Technically, there are another two forces. We're probably not going to need it for this problem, but technically they're there because the box is making contact with a surface. But it's going to have gravity pulling it down. Yeah, sure, the surface is stopping it going through the surface, but we have this force of mg, and we have the normal contact force going up. In this case, the normal contact force would be equal to mg in size because the box is on the ground. It's not like the box is jumping up or going through the table. They would actually balance. Find the frictional force. So as I say, we don't actually need the vertical forces to do this because everything's horizontal for friction. My resultant force I'm going to make going in the positive direction. So therefore, going to the right in my problem is going to be the positive direction. And I'm going to say the resultant force, the result of all the forces. We just write them down. What have I got? I've got friction 1 in the positive direction, friction 2 in the positive direction, friction 3 in the negative direction. Okay. I know the horizontal forces will all result to be 0 because the box is not moving. So I can sub all that in. The resultant force is 0. The two forces they told me leaves me with F3, which is the friction. So the friction is 45 newtons. Okay. Suppose the truck on the left has got a mass of 30 kilos and the truck on the right's got a mass of 50 kilos. The truck on the right is pulled along with a force of 120 newtons. Neglecting friction, so we assume there's no friction in this problem. Calculate the tension in that chain. So a chain we could treat like a string. Note, they've only shown the horizontal forces. Technically, there would be a whole heap of other forces here. You know, each one of these wheels would have a force due to gravity on it. Would also have a contact force going in the opposite direction. But we don't care about that for this problem. So let me just look at the left truck. What's happening with the left truck? There's Bob. And the left truck, we have tension pulling it this way. Tension acts away from the object. So tension is going away from the truck on the left. So it's going to the right. But that's the only thing that's happening because we said forget friction. Not there. So the resultant force on the truck here is simply T, whatever the tension is. Now it's going to be 30A because force is mass times acceleration. So I now know the acceleration of this truck is whatever the tension is divided by 30. Let's have a look at the forces on the right truck. On the right truck, it also has tension. And it's got to be the same value. Because if the string, or in this case the chain, is tight, then it must have the same tension. If they differed, then it would go slack, because one would be less than the other. So you wouldn't have a tight string, or a tight chain in this case. It also has its force of 120 going to the right. Now its force times acceleration, I've called it y double dot in this case. I know it's not vertical and we think y is vertical. I've just picked a pronumeral. And it's got to be different to x because we've got a different object. So my double dot would be 120 in the positive direction, because that's the direction we're travelling, minus the tension. The force in that one would be 50 times acceleration, but what I do know is the acceleration must be the same. Because if the acceleration was not the same, that chain would not remain tight, because one would catch up with the other or something like that. But they're staying travelling at the same. But A we just worked out was T on 30. Sub that in, we get 5T on 3. Rearrange it, bingo, we've got our answer. That's how much tension, 45 Newton. Mass of 2 kilograms. So that's nice when it was horizontal. Let's look at one where it's not horizontal. It's at an angle. It's resting on a smooth plane, inclined at 30 degrees to the horizontal, connected by a mass of 4 kilos by a light elastic string. They always say light, so that way you don't have to worry about the mass of the string in the problem, which passes over a small pulley. There's a picture. So he's talking something like that. Draw a force diagram. Well, let's get all the forces here. Okay. Force 1 I'm going to call here, that's the contact force for the 2 kilogram block. It's going to be at right angles to the surface, so it's going off in that direction. It would have a force due to gravity. Now it doesn't matter that this is on a slope, gravity is still acting straight down. So I've got that happening. The 4 kilo block would also have a force due to gravity on it. And there would be tension going up our string. It's going away from the object. Same in the other one, but they've got to be the same. It's the same string. The only time these could possibly be different is maybe if we tied a knot at the pulley, and then it'd be like they were two different strings, then they could act independent of each other. But whilst it's the same piece of string, they've got to have the same tension. Now, when they say a smooth plane, what they're basically saying is there's no friction. Because if it's smooth, there's no friction. So hence I haven't put frictional forces into my problem here. Find the tension in the string if the 4 kilo block is moving down. I'll look at each object separately. Let's look at the 4 kilogram block. There's Bob. Vertical forces, I've got the 4G going down, I've got the tension going up. So force R4, so the resultant force of the 4 kilo, that's how I've labelled it, so resultant force of 4, the 4 kilo block. That's 4G minus T. But it's going to be mass times acceleration, so 4A is 4G minus T. The 2 kilo block, going to have to resolve this. But I'm going to resolve it a little bit differently to make life easier for myself. Because you see, I want to sub in T. So if I was to break tension into 2 components, I wouldn't get T. I would get T cos 30 or T cos 60 or something like that. Makes life so much easier for myself if instead I resolve in the direction of the plane, or the direction of the tension in this case. Because if you imagine rotating that problem so the tension looked horizontal, then if all I'm interested in is tension, the normal force doesn't come into play because it's at right angles to the tension. Whereas if I leave it like this, then vertically there'll be a component of the contact force and there'll be a component of the tension as well. So let's make life easier for myself. It means in this triangle now, the gravity has to be resolved into what is we're calling horizontal and vertical, which is really down the plane and right angles to the plane. So how would I get to G? I'd go down to the plane and then down there. So there's the direction. I've got to work out the angle. We'd work out that 30 degrees is down there. A little bit of geometry, you can work out where the 30 degrees is. So now, if I look at up the plane on the 2 kilogram mass, then I've got tension going up and I've got 2G sine 30 going down. There's no mention of this normal contact force, which I don't have a value for. So the resultant force on the 2 kilo block will be T minus 2G sine 30, but the 2 kilo block will be 2 times acceleration. Again, the acceleration's got to be the same because it's just moving on this pulley system. If it was different, the string would go slack and it wouldn't happen. Okay, so I have 4G minus T is equal to 2T minus 4G sine 30. Multiply by 2, I get 4A. I'm equating them. I can now make T the subject of this, and I've got an answer for my tension. It's an exact one. Plug it into a calculator, we get 19.6 newtons.